Hi everyone, welcome back to the new year. Before you left on holiday break, you worked up to Chapter 8, which was the pinnacle of your learning. Over the course of the semester, you made so much progress in creating reaction equations. You knew how to write compounds given their names, and you learned how to do stoichiometry after balancing the reaction and calculate how much product you should get given so much reactant. And that's a lot of skill, and you should be proud of yourselves for developing that much ability in chemistry over the course of a semester. Chapters 9 and 10 take a different angle, and ultimately we're looking at how bonds form between atoms. And Chapter 9 first deals with where the electrons are located, so this is called electron configuration, and we're going to identify the shells or the energy levels that the electrons are located in, and this gets us ready to do bonding in Chapter 10, which also deals with shapes of molecules. That prepares us to do solids, liquids, and gases in Chapters 11 and 12. So let's get started. Electron configuration. This chapter begins with the question, why is it that helium blimps are safe and we see them floating at their advertisements above stadiums all the time, but hydrogen blimps, such as the famous Hindenburg, are flammable and not used? What's the difference between helium and hydrogen, both gases and both small atoms or molecules? And we'll come around to the answer to this question at the end of this chapter. Niels Bohr is credited with figuring out that the electrons have different energies within the atom, and he made his discovery based on light and the fact that every element has a unique line spectrum. This is some fundamental physics that we're going to review right now, which is on the electromagnetic spectrum and how light is a small sliver of the electromagnetic spectrum. We need this information to move into the Bohr model. So here we first have an image of the electromagnetic spectrum. So if you look at the scale here, radiation with wavelengths in the range of 10 to the 5th to 10 to the minus 15th meters are within the electromagnetic spectrum. We see Roy G. Biv laid out here. Red light has longer wavelengths than violet light with shorter wavelengths. Correspondingly, red has lower energy, violet has higher energy. And that's because of the relationships between wavelength, frequency, and energy. Here we're looking at a wave. We say light can be both a particle and a wave. Let's consider its wave properties. If you have waves like this, the wavelength is measured from peak to peak or trough to trough. You have to be consistent, but it's in meters. It's a length, wavelength. Frequency is, if we would have a marker here and say these would be waves lapping up onto a boat dock, in a second of time you would count how many waves crashed into the boat dock. So in a second, how many waves pass by? That's what frequency is. How many events per second or waves per second? It's measured in per second or hertz. Visible light is that section of the electromagnetic spectrum in which the rods and cones of your eye respond to the wavelengths of radiation coming in. So we see white light as being comprised of Roy G. Biv, and they spread out in the 400 to 700 nanometer range. The speed of light is given the symbol c, and it's 3 times 10 to the 8th meters per second, or 186,000 miles per second. That is so fast. That means that if you flashed a flashlight on the equator, it would go around the Earth in 1/7 of a second. When you see objects with color, what you're seeing is the light wave that is reflected off the object. That's the wavelength that's coming into your eye. So for instance, this woman's shirt absorbs everything but the red. The red's reflected into your eye. We say the speed of light is 3 times 10 to the 8th meters per second. There is a relationship between the wavelengths and the frequency. C equals lambda nu. This is the Greek symbol lambda, standing for wavelength in meters, and this is the Greek symbol nu, standing for hertz. And remember, hertz are upside down seconds, so it's meters times 1 over seconds, or meters per second, gives us speed is meters per second. So here's a simple problem asking you to relate these new terms, C equals lambda nu. So let's practice this. C is lambda nu. What's our lambda? What is the frequency? I'm looking for nu, okay? And this is my lambda because it is a wavelength. That's my lambda. And remember to convert it to meters before you do this problem. Do you remember what nano's worth? What's a nano worth? Right, 10 to the minus 9 meters. So we're going to simply say the frequency is C over lambda, so it's 3 times 10 to the 9th divided by 400 times 10 to the minus 9th. This ends up being a really large number of 7.5 times 10 to the 14th. What are my units on a frequency? They're hertz. The photon is the particle of light, and it can be viewed as a bundle of energy. The energy of the photon is dependent on its frequency, or inversely related to its wavelength. So we said that red light has longer wavelengths than violet light. So that's why red is low energy and violet is high energy. And you can always keep this straight if you consider the sections of the electromagnetic spectrum. Let's name these. I haven't done this yet. At the low energy end are radio waves. I don't think you've ever been concerned that radio broadcasts are all around you. You're not concerned about the energy embedded in a radio wave. Likewise, we have microwaves. We all have microwaves in our house, and we don't have to shield ourselves from them. They're good for activating water molecules and getting them vibrating, which is how they heat our food. But they're generally not harmful. Likewise, infrared rays are viewed as just its heat. Heat is emitted through infrared, and we aren't concerned about being exposed to that. On the opposite side of visible light, you have ultraviolet. Now we start to protect ourselves, don't we? We protect our eyes from ultraviolet lights because we know that ultraviolet light can cause cataracts, and we definitely limit our exposure to X-rays, and we never want gamma ray exposure, although we can't avoid some of it that comes in from the sun. Alright, so let's practice with this a bit. We have 3 types of radiation that we're going to consider: visible light, X-rays, and microwaves. Of these, let's rank them by wavelength, frequency, and energy. Alright, first by wavelength. Which has the longest wavelength? Visible light, X-rays, or microwaves? Okay, if you think of the order of them on the diagram, microwaves have longer wavelengths than visible light, and X-rays were short wavelengths. Then frequency is inversely related to wavelength. When wavelength goes up, frequency goes down. So we'll just change the signs on these, and that's the correct order. X-rays will have the highest frequencies, microwaves will have the lowest. And then energy per photon. Energy is directly related to frequency. So X-rays will have the high energy, microwaves will have the low energy. Spend some time memorizing the sequence on the electromagnetic spectrum so you can keep straight the low and high energy sequence. All living creatures emit in the infrared. Snakes can see infrared. Infrared cameras notice infrared. Red sections are areas of warmth. At the high end, we have X-rays and gamma rays, and they are used for cancer treatment, as you know. They knock apart the atoms that they strike, And if we target them on tumors, we can break apart the molecules comprising those tumors. We also hope to destroy the DNA structure of the tumor so that it can't replicate. So before we go into 9.4, let's come around to the question of why is hydrogen so flammable and helium is inert? And it has to do with the electron structure. We're going to move now into the Bohr model, and light had an important role to play in Bohr's ideas about the electrons being different in energies. It turns out that hydrogen's electrons configuration, it's not yet stable, so it's highly reactive. But helium has a complete filled shell and makes it inert, and it won't react with the oxygen in the air. We'll get into this in the next video.